I'm Alberto Vilariño, and I'm developing my PhD called Advanced Road Vehicle Design, Machine Learning-Based Aerodynamic Shape Optimization under Carlos San Miguel and Rodrigo Castellanos' supervision. And what we are going to talk today, we're going to talk about automotive aerodynamics and why this is important. Basically, we've got three main reasons. One is efficiency, so an aerodynamic car consumes less, happy days for everybody. Stability. The aerodynamic forces can make handling or the car unstable, so aerodynamics keep you safe. And passenger comfort, because basically if there are loads, it could be, the wind noise, it could be quite stressful inside the cabin. Within the constraints in the design, we've got design, we always have design, engineering requirements, including budget and packaging, everything has to fit. So historically, aerodynamics appears in automotive industry in the 900s, but it doesn't become mainstream until the 50s, 60s. And for all this time, aerodynamics development has been always the same. No major changes on the way that we develop cars. We go, we try, error, try again, and so on. And that is a bit of a problem, especially nowadays, and that gives us opportunity. The times for any project in the automotive industry, and I suppose in most of the industries, they are shrinking down. We need faster answers, much quick. And we've got a new tool, which we all know now, ML, AI, appearing, and we can use that to help us to develop better products in less time. So the question here is, can we use ML to explore 3D vehicle designs, keeping the vehicle as it is, all the constraints in place, and make faster decisions? And this is what I will be exploring over the next years. So this year I did a bit of literature review again, and I've seen an interesting shift on what things has been a year and a half ago and how things are now. A year and a half ago, we were seeing a lot of work into ad hoc CFD optimization. There was plenty of publications, but more recently, what we are seeing is a lot of databases, at least in the automotive world. Plenty of them. We've got DriveNet with 8,000 cars, Drive AirStar with 12,000 cars is gigantic. And that has an effect. Most of the works that we are seeing now, they are surrogates. We are seeing a lot of surrogates getting flow data, CD, out of these data sets. So the question now is no longer if we can predict drag. We know it's possible. All of those data, I didn't mention it, all of those data is runs. So that's possible. Now the question that we want to answer and where we will be focusing, because there is no much work right now there, is if we can combine ML, high fidelity physics, a constrained design for a global optimization. And I stress on global because most of the work doesn't cover that. So for doing that, I spent this year a lot of time looking on how you parameterize a car. And that is not trivial. A car is a 3D shape, very complex geometry. So after researching on the available literature, I came out with around 65, it's more or less, a number of parameters to define a car. On this study is not just defining the parameters, I also look into the constraints, how those parameters interact with each other, the dependencies, and also the importance they've got into the vehicle aerodynamics, because definitely there are things that are more important than another. And also the complexity of implementing that parameterization on the final design. Alongside with that, I've been looking into how to make this parameterization, and the answer is morphing. Is the best option by far, extremely used in literature, and basically it's used because it's fast, it's easy, and preserves the final shape of the car. So you change the car, but it still looks like a car, looks like the original car, which at the end is what you want. You don't want to start with a bang and end up with a sports car. That's a nuisance. It's out of the work. The car that I selected for the study is the Driver. It's an open source geometry developed by the University of Munich, extremely documented, and it's realistic. So we bridge the gap between very simplified vehicles or shapes like the Ahmed body, and we go towards something more realistic. So the next step is clear. Choose some of those parameters, put them in a LES CFD and create a validation loop for the whole workflow. And I say LES because we are going behind the idea of just optimizing CD. We are looking into not only the averaging number, but also the transient structures, how they can affect. Because we know that we can have the same drug with different flow structures. So we want to look into the detail why that drug is happening. That's why here, what do I have here? Okay, I don't know how to do it. I think here. We've got here the flow, which will be our LES solver. We want to give the ML the best results so the data wouldn't be biased by smoothing too much the information we are giving it if we use runs approach. So the other bit I've been doing this year quite a lot is working on the toolbox. So from the pre-processing overall, I select ANSA as the primary tool. ANSA will be responsible for meshing, morphing the card, so modifying the card and generating the mesh. I work extensively on it, clean the geometry, and I've got the meshing and morphing strategy ready, and they are fully automated, so quite a lot of work on there. The other bit is the CFD solver. I choose a SOT2D developed by our colleagues from Barcelona Supercomputing Center. It's a high-fidelity LES, GPU native, so it's extremely fast. It's really well connected in HPC and AI, and it has been already used for automotive aerodynamics with really good results. From the side of the AI agent, Haigu will be the selected one initially. For several reasons, it's a really nice genetic algorithm with great exploration and exploitation, but also because it's a carryover from the work I did last year in a 2D problem, so the knowledge I've got on it is really set. With that, this is the achievements for this year. So I've got established and well-documented workflow. I have a vehicle fully parameterized, which has been challenging, and I have evaluated the different the different software tools. Regarding the dissemination, the work from last year has been presented in Eurogen 2025, and this year is going to be presented in the World Congress of Computational Mechanics. Out of that work as well, we've got a paper that I co-authored, and I did a bit of a presentation, a bit more informal, in Tata Consultancy Service Siemens in a forum for AI in industry. What I'm doing right now, aside from presenting, it's basically finalizing the work in the CFD world, and the next step is going to do this complete implementation of these three tools on the workflow. And then after that, the next step is start to leverage that physics-based data to improve the agent performance. So introduce transient data into the agent, so the decisions will be much more informed, and we will be exploring different ways of improving the vehicle with that transient fluid. And then in a much longer term, looking into other agents to see what kind of results we can get out of that. And I finish in time this time. Yay.